Hello, today we're going to look at the use of cumulative probability tables for the binomial and Poisson variables, which are all discrete random variables. Usually, they would ask you to calculate the probability that your random variable value lies within a given range. If that range is lengthy, then you would have to do a lot of calculations to arrive your result, and it might be time consuming during the exam. So the cumulative probability tables help in such situations by shortening the length of your calculation. So you should have to pay attention in order to get how these tables are helpful in shortening your calculations. Now, before we start, we have to note that the binomial distribution has the notation where n and p are the parameters of the distribution, with n being the number of trials and p being the probability of success. Now, the random variable which follows the binomial distribution can take values ranging from 0, 1, up to n, the number of trials itself, and its probability mass function is given by n combination x cure to the n minus x, where cure is the probability of failure, such that p plus cure would always be 1, and then times p to the x. In the case of the Poisson variable, we have the notation where lambda is the mean of the distribution, and it can take values ranging from 0, 1, 2 up to infinity. Now, the probability mass function for the Poisson distribution is given by e to the negative lambda, lambda to the x, all over x factorial. As already said, each time you have a calculation that involves either a binomial distribution or a Poisson distribution, there would be a range of values of x that the random variable can take, and they will be asking you to calculate the probability that the random variable can take a value in that range. And if you have a large range of values, then your calculation would have to be lengthy, and this is where cumulative probability tables would come in to shorten your calculation. Now, before we proceed, we would have to know what is meant by cumulative probability. Actually, cumulative probability simply means the sum of the probabilities from the smallest possible value that the random variable can take up to and including a particular value. So if I have p of x less than or equal to a, then that p of x less than or equal to a is the cumulative probability value for the random variable value a. And this normally has to be p of x equals 0, the lowest that the random variable can take, plus p of x equals 1, plus p of x equals 2, plus the rest of the probability values, plus that of a itself. So this calculation, as I've already said, if a is a large number, for instance 7, means that I have to sum up 7 calculations, and this usually, as I've already said, is so lengthy in such a way that it will be time consuming during the exam. So to proceed with our use of the table, I would first demonstrate something here so that you understand what will be happening as we are manipulating the various calculations. Consider the probability distribution in which we have a random variable and the probability values it can take, where it takes values from 0, 1, 2, 3, up to 4. The various probability values are 0.10, 0.20, 0.30, 0.25, and 0.15. Now we can proceed to calculate the cumulative probability values for each of those values. Let us call it f of x. In the case of 0, its cumulative probability value is simply its probability value, because there is no other value to the left of 0 to add to have the cumulative value. In the case of the cumulative probability value of 1, I'm going to sum up that of 0 and that of 1. So I will have 0.30. In the case of the cumulative value of 2, I would sum up that of 0, that of 1, and that of 2. And that would simply be the cumulative up to 1 plus the probability of 2, which will be 0.6. And to have the cumulative of 3, I would sum up the probability values from 0 up to 3, which is simply cumulative probability value of 2 plus the probability of 3, which gives you 0.85. And then to have the cumulative probability value of 4, I would sum up the probability values from 0 up to 4. And you would recall that for any random variable, the sum of all the probabilities should give a 1. So I expect that the cumulative probability value of 4, which is the last value that the random variable can take, should be 1. And actually it confirms, because when I take the cumulative probability value of 3, which is 0.85, and I add the probability of 4, which is 0.15, I will now get 1. So from this table, if I have to find the probability that my random variable takes a value less than or equal to 0, it would simply be the probability of 0 itself, which is 0.10. If I had to take the probability that x is less than or equal to 3, I would have to sum up the probabilities x equals 0 plus probability of x equals 1 plus probability of x equals 2 plus probability that x equals 3. And you can see that it is the same as just getting the probability that x is less than or equal to 3 from tables. And the tables already provide this capital F of x, the cumulative values, which have been pre-calculated and presented on the table, so that each time you need them, you just go and read the values. And that corresponds to 0.85 from the cumulative probability distribution table. So in the case where I would need to find the probability that x equals 2 from my cumulative table, I would simply take the probability that x is less than or equal to 2. That means the sum of the probabilities up to and including that of 2 minus the probability that x is less than or equal to 1, the next lower integer to 2. At this point now, I get the cumulative value of 2, which is 0.6, minus the cumulative value of 1, which is 0.30. And that gives us 0.30, which actually corresponds to that probability value. In the case where I needed to calculate the probability that x lies between 2 and 4, means I have to sum from 2 up to 4. And to do that, what I would simply do is I take the sum up to 4, from 0 up to 4, minus the sum of the probabilities from 0 up to the next lower natural number that is not involved in that sum, and that is 1. So when I get the sum of the probabilities from 0 to 4 minus the sum of the probabilities from 0 to 1, I will now get the sum of the probabilities from 2 to 4. And that gives 1 minus 0.3, which gives 0.7. If you had to do it the other way around, by summing the probability values up, you would have 0.3 plus 0.25 plus 0.15, and it corresponds to 0.7. Now, in the case where I had to find p of x less than 3, I would have p of x less than or equal to 2, because again I must have to include the equality sign so that the cumulative value of 2 can be used. And from the table, the cumulative value of 2 is 0.6. In the case where I had p of x greater than 3, I would have to put 1 minus p of x less than or equal to 3. And the aim here is that I should use the cumulative tables without having to do any calculation. So with this now, I have 1 minus the cumulative value of 3, which is 0.85. And that gives 0.15, which actually corresponds to the probability of x equals 4 on the table, because x greater than 3 means we are only left with the variable value 4 to calculate the probability, which we just needed to read from the table directly as 0.15. In the case where we have p of x greater than or equal to 2, the table only has probability values that are cumulative. That means that have less than or equal sign. So since this is greater than or equal, I'll first take 1 minus p of x strictly less than 2. It gives the same value. So we have 1 minus p of, now here it is strict. We must make sure that it is having the equality according to the cumulative definition. Since the cumulative values must include the equality sign, I will now take the next lower integer of 2, which is 1, so that I can now find the probability by taking the cumulative probability of 1 and subtracting from 1 to have the result. The cumulative probability of 1 on the table is 0.30. So we have 1 minus 0.30, which gives 0.70. Finally, before we go to the tables, a summary of how you would be preparing your solution before going to the tables. If you have to do a calculation which involves x equals a, you would have to do p of x less than or equal to that a minus p of x less than or equal to a minus 1. So that ensures that you have the cumulative of a minus the cumulative of the next lower integer to the left of a. In the case where you have p of x less than a, you would have to first make sure that your inequality sign includes the equality. That would simply be p of x less than or equal to a minus 1, as we already saw in the example demonstrated above. In the case where you have p of x greater than a, you remember that the sum of the probabilities of the various values that the random variable can take is always 1. So if the random variable values are greater than a, it means that those that are greater than a plus those that are less than or equal to a would always give 1. Since we need the inequality sign to be less than or equal to before we can go to the tables, we can then take a turnaround by taking 1 minus the probability that x instead takes a value less than or equal to a. It will give the same result as the probability of x being greater than a. And from here, the cumulative of a can now be read from the table, and then the calculation done without any difficulties. In the case where we have p of x greater than or equal to a, so it means that if I take 1 minus p of x less than a, it should give me the same thing as P of X greater than or equal to A. So here now, the aim again is to make sure that your inequality sign is less than or equal to. So I will simply take 1 minus P of X less than or equal to the next lower integer to A, which is A minus 1. And from there, I can now go to the cumulative tables and do my calculation without any difficulties. In the case where we have to calculate the probability that X lies between A and B, where B is greater than A, then we simply take the cumulative value of B minus the cumulative probability of the next lower integer of the lower limit in the boundary, which is A minus 1. This ensures that we have in our calculation the sum of the probability values from A up to B inclusive. Now, in the case where one of the boundaries has not been included, you adjust it so that it should be included before you can apply this other format that has been presented here. Now, in the case of binomial tables, consider a binomial distribution with parameters 10, half. If I have to do calculations with a binomial distribution that has 10 and a half as the parameters, so you can see the table, cumulative binomial probabilities. The table has tabulated values of P of X less than or equal to R. So R here is like the lowercase x that we use to denote the value that the random variable can take, where X has a binomial distribution with parameters N and P. So on this upper row, we have values of P, the probability of success. And you can see they start from 0.05 up to 0.5. On the extreme left column, we have the value of N and then the X value that you need to calculate its probability. So when N is 4, it is possible that you calculate the probability that R or X is 0 or 1 or 2 or 3. And when N is 5, you have 0 to 4 possible values of X that you can calculate. When N is 6, you have 0 to 5 possible values of X that you can calculate at that point. N equals 8, you have X equals 0, X equals 1, X equals 2, up to X equals 7, up to where N equals 10. You can have 0, 1, 2, 3, and so on, up to 9. If I were to apply this particular one and I needed to calculate P of X equals 5, with the case where my binomial distribution has parameters N equals 10 and P equals half, my P of X equals 5 using tables without going to the probability mass function would be equal to P of X less than or equal to 5 minus P of X less than or equal to the next lower integer of 5, which is 4. I will now go to my table where N is 10. I'll be dealing with this lower section of the table. The values of P appear at the upper first row there, and my P in this example that I've chosen is half. Half is 0.5. So I'll be reading X values where P is 0.5. Now, when I come to P of X less than or equal to 5, I will locate 5 on this lower part of the table. So I would follow up from the row having 5. Then I take vertically from my P value down, and the cumulative probability value would be where the two have intersected, and this is the value. which I can now write down as 0.6230. For the cumulative value of 4, I will locate 4 on the extreme left and follow up. Take now from the top row till where they would intersect, and they are intersecting at this value here, which is 0.3770. So I would say minus 0.3770, which gives 0.2460. Suppose I wanted to calculate P of x greater than 3, it will be the same as 1 minus P of x less than or equal to 3. And so I need the cumulative value of x equals 3. I'll go to the table where n again is 10 because I'm still in the same question, and p in the upper row is 0.5. Then I locate where r is 3, which is representing x there, and I move horizontally and then vertically from my value of p to where they would intersect. They intersect here where the value is 0.1719. So I would now say 1 minus 0.1719, which gives 0.8281. And you have to support your answer by saying from tables. Very important. Each time you have obtained your values without doing the calculation, but by going straight to the table, you have to tell the examiner that you have used but tables to get it. Otherwise, you might lose marks. So always write from tables each time you have used the cumulative table. Finally, if I had to calculate P of 3 less than or equal to x less than or equal to 6, that will be equal to P of x less than or equal to 6 minus P of x less than or equal to the next lower integer of 3, which is 2. And from there, I go to the table and read the cumulative probability of 6, which I would go again here. I take horizontally from 6 and then vertically from my value of P till where they intersect. They intersect here at 0.8281. So I write 0.8281 minus, I take the cumulative of 2, which is 2 here. I locate it on the extreme left and draw a horizontal line till I meet the line, the vertical line from my value of P at the top, and that corresponds to 0.0547. So I write 0.0547, which upon subtraction gives 0.7734. And again, you have to write from tables to back up your answer. Finally, we look at the case involving cumulative Poisson probability tables. Again, that, as we already saw, has to be used when we are dealing with a cumulative probability. So we must have had a relationship of the form P of x less than or equal to r, or P of x less than or equal to x, for a Poisson distribution with parameter lambda. As you can see, the table here is not as complicated as that of the binomial distribution. We have at the upper row the values of lambda. So if the calculation involves 0.5 as lambda, then the column you would use is here. If it involves 1.0, 1.5 up to 5.0, in the upper portion of the table. Now in the lower portion, we have values of lambda again, continuing from 5.5 up to 10.0. In the first column of the extreme left, we have the values of x, which are denoted here as r, that the random variable would take. Then once you have located your value of lambda at the top row of your table, then you locate your value of x, which you wish to get the cumulative probability value, on the extreme left of the table, and then drawing a horizontal line from your value of x and a vertical line from your value of lambda, where they would intersect. The value that you obtain there is the cumulative value of the particular value of x or r that you were seeking to find. And now, to demonstrate the use here again, let us consider a Poisson distribution with parameter 4. That means the mean of the distribution lambda is 4. Here I might be required to find the probability that x is greater than 5. Then it means it has to involve the probability that x is greater than or equal to 6. And for a Poisson variable, the range of values that the random variable can take are from 0 up to infinity. So we have to make a turnaround by taking instead 1 minus the probability that x does not take any of those values. Greater than 5 means from 6. So the other way around would be from 5 down to 0. So x less than or equal to 5 would be the alternative to do the calculation. And luckily here, x less than or equal to 5 gives the cumulative probability of 5, which means I can now go to the table to read that value. To read the value from the table, I'll first locate the value of lambda at the top uppermost row. The value of lambda 4 is located there, and then on the left hand side, the extreme left, I will locate the value of x that I am looking for, its cumulative probability value, here 5. So 5 is here, and then now I draw a horizontal line from that 5 and a vertical line from my lambda so that I get where they intersect, and that gives me the cumulative probability value of 5, which is 0.7851. I can now complete my calculation by subtracting 0.7851 from 1, and that gives 0.2149 from tables. Always write this from tables in order to indicate where your value is coming from, because you have shortened the calculation. Finally, before we conclude, you could be asked to calculate the probability that x lies between 3 and 7. In that case, I will need to have the cumulative value of 6, because actually 3 and 7 not included. It means the boundaries are 4 and 6. So I'll take p of x less than or equal to 6 minus p of x less than or equal to 3, so that the sum up to 6 minus the sum up to 3 will now include the sum from 4 to 6. So the cumulative of 6, I'll go again to the table where lambda is 4 and x equals 6. Allocate the value. They intersect at 0.8893. So I put 0.8993 minus the cumulative of 3. Go from 3 horizontally to where there is the intersection of the mean 4, which corresponds to 0.4335. So 0.4335 giving 0.4658. from tables. Thanks for watching. In the next video, I'm going to treat the case of the use of normal distribution tables, and it is usually the most important because it appears almost in every exam involving further maths or statistics.